We use the word energy all the time. A moving car has energy, water stored behind dam has energy, and a compressed spring has energy. They look completely different, but there is something common behind all of them. Energy can move from one object to another, and it can change from one form to another. And this immediately gives us today's central question. When energy changes form, can some of it simply disappear? Before answering that, let's identify a few important ways mechanical energy can be stored. In my other video, I explained three types of mechanical energy. For example, if I threw a ball, its motion gives its kinetic energy with this formula that show kinetic energy depends on velocity squared. Assume I lift the same ball upward, and energy is now associated with its position in Earth's gravitational field. Now I compress a spring. We can store energy in its deformation, and the elastic energy deformation is given by this formula that I explained its derivation in my previous video with link in description. Now think about something we all do every day, charging a phone. Electrical energy enters through the charger and it is stored in the battery as electrochemical energy. Later, the battery supplies electrical energy to different components. The screen transforms electrical energy mainly into light and heat. The speaker transforms electrical energy into mechanical vibration and then sound. The microphone works in the opposite direction. Incoming sound causes mechanical motion in the microphone and is converted into an electrical signal. And some of energy ultimately becomes thermal energy in the electronics. So when the battery percentage drops, the energy has not simply vanished, it has been transferred and transformed. Is this just true for phones, or is it a fundamental law of nature? This is actually conservation of energy principle. If we define our system carefully and account for all forms of energy, the total energy remains constant. But there is an important distinction. Total energy conservation is the fundamental principle. As an example, mechanical energy conservation is given by this formula, in which is a special case. Sum of kinetic energy and potential energy remains constant. It works when energy is not being transferred into thermal energy by processes such as friction or drag. Let's see that special case happening in front of us. Let's release the ball from rest. At the top, its speed is 0, so its kinetic energy is 0. But because it is elevated, its gravitational potential energy is also maximum. Now watch the bars. As the ball falls, the green potential energy bar decreases. At exactly the same time, the red kinetic energy bar increases. But look at the blue bar. Total mechanical energy does not change. The potential energy hasn't disappeared. It has become kinetic energy. Height is being exchanged for speed. But what happens when friction or air resistance is present? Does energy conservation fail? In our previous free-fall example, we assume no air resistance. Potential energy decreased, kinetic energy increased, and their sum remained constant. Let's still look at only on mechanical energy and add the friction as a non-conservative force. Now, we need to be careful with the phrase non-conservative force. Friction is non-conservative, but this does not mean that energy is no longer conserved. If non-conservative forces do work, the mechanical energy changes as given by this formula. Without friction, for mechanical energy, energy can move back and forth between kinetic and potential energy, while the sum remains constant. Friction acts, in this case, opposite to the displacement. So, it does negative work on the moving objects. If the friction force is approximately constant, the work done by friction is given by this formula, where Fk is the kinetic force and its formula is given by this relation. Here, mu k is the coefficient of kinetic friction and n is the normal force. Because this work is negative, the mechanical energy E kinetic plus E potential decreases. But this does not mean that energy has disappeared. The missing mechanical energy is transferred mainly into internal or thermal energy of surfaces, with some energy also appearing as sound and deformation. So this is the important distinction. Mechanical energy is not always conserved, but total energy that accounts for friction loss is. In the previous slide, we saw that friction causes mechanical energy to decrease because the energy is transferred into heat, sound, and deformation. But there are two different questions we can ask. How much energy is transferred? How fast is it transferred? The first question is about work or energy. The second question is about power. So, power is simply the rate of energy transfer, or the rate at which work is done. It's given by this formula, the change in work divided by change in time. If, for example, 100 joules are transferred in 10 seconds, the power is 10 watts. If the same 100 joules are transferred in only 1 second, the power is 100 watts. So, more power does not necessarily mean more total energy. It means the energy is being transferred faster. In this slide, I'm going to end this presentation with an example. We have two cars with different aerodynamic characteristics and size. We want to calculate the rate of mechanical energy lost due to air resistance for two different speeds, 60 km per hour and 120 km per hour. We already know that air resistance removes mechanical energy from the car. The rate is simply power as given by this formula. For cars with effective area CDA, in which CD stands for drag coefficient, the aerodynamic drag force is approximately given by this formula. FD equals 1/2 rho air density CD drag coefficient A cross-sectional area V velocity squared. Since power is force times velocity, we get power as the rate of mechanical energy loss as given by this formula. This V cube dependence is the key result. Now first let's move to EV1. For the EV1, the effective area CDA is 0.37 meter squared. At 60 km per hour or 16.7 meter per second, the aerodynamic power is about 1.03 kilowatt. Now assume we double the speed from 60 to 120 km per hour. Because power depends on V cube, so the aerodynamic power becomes about 8 times larger. Now for the second car, H2, its drag area is much larger. CDA is equals 2.45 meter squared compared with the EV1. So at the same speed, the H2 requires about 6.6 times more power just to overcome aerodynamic drag. That gives approximately 6.8 kilowatt at 60 km per hour and 54 kilowatt at 120 km per hour. To summarize, the key result of this example is that aerodynamic power increases with cube of speed. So, doubling the speed requires about 8 times more power to overcome air resistance. Vehicle aerodynamics also matter greatly. A larger effective drag area means substantially greater energy loss at the same speed.